In this series of lessons so far, we have investigated the properties of different materials and discovered that there is a link between these properties and the microscopic arrangement of particles that make up the material. We have also identified the simplest form of matter as an element. Elements have different properties because of the nature of their atoms and because of the way these atoms are arranged. Up to now, we have seen how metal atoms are held together in a metallic bond and how non-metal atoms bond covalently to form molecules. I've also mentioned that most elements are not found in nature in their pure form. We find them bonded chemically to other elements to form compounds. Now, these compounds have a huge range of physical properties that are very different to the physical properties of the combining elements. How do we explain this? In order to explain the different properties of compounds, we once again need to look at how the particles in a compound are arranged. So, by the end of today's lesson, you should be able to identify the types of bonding found in compounds and explain the physical properties of compounds using models of the microscopic arrangement of particles. Do you remember when Aaron let sodium and chlorine react in the laboratory? He heated sodium until it melted and then plunged the glowing metal into a gas jar of chlorine. After the reaction, we noticed that white crystals had formed as the product. The sodium and chlorine combined to form a new substance that is no longer an element but a compound. The white crystals also have a new chemical name, sodium chloride. The name sodium chloride tells us that this substance was made from sodium and chlorine. To show this, we can write a chemical formula made up of the symbols of the elements, NaCl. The common name for this compound is table salt. Now, what about the physical properties of this compound? We already know that table salt has some very different properties compared to the elements that were used to make it. For one thing, chlorine is a poisonous smelly gas and sodium is a very reactive shiny metal, but we can eat salt. You should also notice that salt forms a white crystal that is harder than sodium, but is brittle and easily crumbles. I wonder if this compound conducts electricity. Let's check by doing a simple experiment. I have set up a circuit board here on the desk. If I place an iron nail into the circuit, the light bulb glows brightly. Now, I'm going to replace the metal with this salt crystal. Do you see that the light bulb does not even begin to glow? So, as a solid, sodium chloride does not conduct electricity. It would seem that this compound has many physical properties similar to the solid nonmetals, such as sulfur or phosphorus. But there is at least one difference that I'm sure you are all familiar with. When sodium chloride is placed in water, it dissolves to form a saltwater solution. Solid nonmetals like sulfur and phosphorus never dissolve in water. So, the compound sodium chloride is different from nonmetals after all. There's one final little experiment I want us to do with the salt. Can you predict what would happen if I connected the saltwater solution into my electric circuit? Will the light go on or not? Let's see what happens. The light goes on. The salt water solution is a conductor of electricity. To explain these properties we've discussed so far, we will need to look inside the salt crystals to see how the atoms of sodium and chlorine have combined. The sodium atoms that make sodium chloride all have 11 electrons and 11 protons. The outer electron is found far away from the nucleus. When sodium reacts, it gives this electron away to form a positively charged sodium ion. We write this as Na+. The chlorine atoms gain the electron that sodium has lost to form a chloride ion, written as Cl-. Whenever any positively charged particles are brought close to any negatively charged particles, there will be strong forces of attraction between them. During the chemical reaction of sodium and chlorine, billions of ions of sodium and chlorine were packed and formed together in a regular repeating pattern to form a single crystal. We recognize that there is a chemical bond between the ions, so we call this ionic bonding. Now, it is not only sodium and chlorine that combine in this way. Whenever a metal element reacts with a non-metal element, this same sort of crystal forms. I'm sure you must be wondering how we can use the model of an ionic bond to explain the physical properties of crystals, like sodium chloride. Perhaps you have some ideas that you could discuss with a group of classmates. Explain why sodium chloride is brittle, a non-conductor of electricity, dissolves in water, and conducts electricity when dissolved. Have a look at this model of a sodium chloride lattice. Can you see that all the ions are arranged in layers? If a strong force is applied to this crystal, it can easily crack along these lines. There are no particles to hold these parts together. If the applied force is bigger than the force of attraction, the crystal cracks. So what about sodium chloride's strange electrical properties? Remember that when a substance is a conductor, there must be the movement of charged particles. In a solid sodium chloride crystal, there are lots of charged particles. The sodium ions are positively charged and the chloride ions are negatively charged. But these charged particles cannot move. The electrostatic forces of attraction between the ions hold these ions in a very rigid lattice. That's why this compound is not a conductor as a solid. But if it were possible to weaken the forces between the ions, then these charged particles could move quite freely. That's exactly what happens when salt is placed in water. The water molecules surround each of the ions and pull the lattice apart. Now, when the salt water solution is connected into an electric circuit, the Na+ and Cl- ions can move and conduct electricity. It is important to note that if you heated sodium chloride until the crystal melted, the ions would also be free to move, and this molten form of sodium chloride would conduct electricity. In fact, this is the distinguishing property of all compounds that have an ionic bond. When a metal and a non-metal bond ionically, the compound that forms will not conduct electricity as a solid, but will conduct electricity when the solid melts or when a solution is made. But not all compounds are bonded ionically. Non-metal elements can also bond with other non-metals or with metalloids. These elements may combine differently to the way metals and non-metals bond with each other. Take a look at this quartz crystal as an example. Quartz is a compound made from silicon and oxygen. Remember, silicon is a semi-metal found in group 4 of the periodic table, and oxygen is a non-metal of group 6. This crystal is much harder than ionic crystals. If we were to hammer it, it would crack, but it is not as brittle as ionic solids. Do you think that this crystal would conduct electricity? Why don't we put it into our circuit board to find out? When quartz is placed into our testing circuit, the light bulb doesn't glow. This confirms that quartz is an insulator. But will it conduct electricity when dissolved or molten? Well, quartz does not dissolve and only melts at very high temperatures. Even at these temperatures, it will not conduct electricity. I think we have enough evidence to say that the atoms of this compound must be arranged in a different way to the salt crystal we looked at earlier. It's time to check out what's happening at a microscopic level. When nonmetals combine with other nonmetals or metalloids, they share electrons to form molecules. This type of bond is called a covalent bond. Sound familiar? Yes, it is the same chemical bond we discovered when we looked at the diatomic molecules of some of the non-metal gases. In a quartz crystal, silicon combines covalently with oxygen to form a giant molecule. Inside this molecule, every silicon atom is bonded to 2 oxygen atoms in a spiraling ringed pattern. This bonding is not based on electrostatic forces of attraction, but on the sharing of electrons between the different atoms. We saw this type of covalent bonding before when we looked at the structure of the diamond. But how does this model help us explain the physical properties of quartz? Quartz is hard and not as brittle as a salt crystal because the covalent bonds in this crystal are stronger than the ionic bonds formed in a salt crystal. We can also explain why quartz is not a conductor of electricity. In this giant molecule, all the electrons are tightly held and cannot move. Even when the substance is heated, the electrons are not free to move. The quartz remains an insulator. Some very useful natural materials like cotton and wool also consist of these large molecules. And man-made materials like plastics and nylon were created as a result of elements being combined covalently to form giant molecules. Interestingly, these large molecules all contain the element carbon, which will be studied in more detail in grade 11 and 12. What is important to remember is that whenever nonmetals combine with each other, a covalent bond forms. The structure that forms is a molecule. These molecules can be giant structures or as simple as 3 atoms bonded together, like water. Carbon dioxide is another example of a compound that has small molecules. A carbon atom bonds covalently with 2 oxygen atoms to form a molecule. At room temperature, carbon dioxide is a gas because the intermolecular forces are very weak. The molecules can move away from each other and are not held together by the strong intermolecular forces found in water. When the temperature of carbon dioxide gas is decreased, the molecules move slower because they have less kinetic energy. Slower moving molecules are more affected by intermolecular forces, and at -6 degrees Celsius, the molecules pack together into a solid. The molecules in the solid are held in position by the weak intermolecular forces. We call this solid dry ice. And here I thought that all ice was made up of very cold water. On that note, here is your task for today. The amazing thing about dry ice is that it never melts to form a liquid because the intermolecular forces are very weak. It is also important to note that dry ice is brittle and not a conductor. Can you explain why dry ice has these physical properties? In this lesson, we have focused on the properties and structure of different types of compounds. Compounds are all pure substances, just like the elements. Even though these pure substances have a range of useful properties, do you think it is possible to further combine them and their properties to find better materials? Join us for our next lesson when we reflect on people's quest to find the ultimate material.
Yeah.